Okay, so now let's go ahead and do an example. So we're going to try to compute the surface integral for the vector field f equal to xy I hat, z j hat, x plus y k hat, and s the surface of a plane x plus y plus z equals 1 in the first octant. Oriented upwards. So we're again integrating a surface area over a plane, but in this problem, they haven't given us that nice but only think about it over this box 1 less than or equal to x less than or equal to 2. We're going to go back to that tricky way of solving for the region R where the XYZ planes cut off the plane, and we're integrating over a vector field F. So my surface is this x plus y plus z equal 1. And I'm going to rearrange that as z equal to 1 minus x minus y. Like I said, I'm going to end up using that in 2 places. I'm going to use that when I replace my vector field and when I compute my normal vector. So that's the g of xy in our steps. And my region R is going to be where x plus y plus z is cut off by the coordinate systems. So let's sketch a little picture. I'm thinking about here's my plane. And there's my region. And so we've done this quite a bit before. That region happens to be where z is equal to 0. So it's bound by the line y equal 1 minus x. And then if I want to find my x intervals, I know that x starts at 0 right here and goes up to some value right there where the line y equal 1 minus x hits the x-axis. So then I just have to set 0 equal 1 minus x. Oops. Okay. Which tells me that x equal 1. So my bounds for x are from 0 to 1. This is kind of like old stuff for you. We learned how to do this and practiced it a lot with surface area problems. So those are the bounds for our region R down there. Okay, and then we have to identify our vector field as our third step. So it's the thing that we want to integrate in the end, and conveniently enough, it tends to be the only vector field given to us. Oops, let's keep doing this where I write out all the words. So there's our vector field. But I have to remember that any of my 3D variables z should be replaced by their definition in terms of the surface. So this actually becomes xy, 1 minus x minus y, x plus y. So where I saw z, I just replaced it with my definition of my surface. And then my normal vector, I compute using this formula, and that also uses my definition of my surface. Negative g sub x, negative g sub y1 using partial derivatives. So g sub x here is -1, so I get +1. G sub y is -1, so negative times negative, I again get +1, and the last component is 1. And so this kind of like formula we use backs up the standard orientation that surfaces will have, which is upwards. So technically something normal to the surface could point that way or that way, and we've just selected the one that points up. If somebody told you it had to be oriented down, then you would just have to like take the negative of your normal vector. Okay, and then now we're sort of good to plug it. Oh, sorry, I did say we would compute the dot product separately, so let's do that on the next page. So I can't remember what f was, but I know that n was 1, 1, 1. So we're taking the dot product of xy, 1 minus x minus y, x plus y. That's our f dotted with our normal vector n. And when we take that, we'll just get xy plus 1 minus x minus y plus x plus y, which just becomes xy plus 1. And now we're good to go ahead and plug everything into the formula, which is that the surface integral over some surface f of S of a vector field f is going to be the double integral over the region R of f dotted with n evaluated over the area of R. And so we just found our f dot n. Go ahead and do that there. Our f dot n was xy plus 1. And our region R, we found before, should be this. Y going from 0 to the line 1 minus x, x going from 0 to 1. And then at this point, this is a 2D integral that I know you could solve. So again, I'm not going to show it to you just because the setup is really the tricky part in this section. When you get to this point, it's always good to just make sure that there are no z's inside your integral, or even just in general, make sure that there are no variables in here that you don't deal with when you integrate with respect to the two variables you picked. So if you had one of those ones where it's easier to integrate it over circle-like shapes, you could go ahead from this point and convert it to polar, but then you would have to make sure to convert that and these as well. So just even though the setup for these problems takes quite a while, once you get to this point, it's just like any other integral where you want to make sure those same rules apply. Every function that's in here is integrated against. Bounds make sense for the specific variables that you have and the order you treat them in.